Yes, thanks.
Where's your iPad? What's the name of your iPad?
It's the same as, it's just my name. It should appear as like a second me, I think.
Oh, okay, I see. It should be fine now.
Great, thank you.
Okay, so we continue with the next talk of this section by Andrzej Pokraka about the duals of Feynman integrals. So I'll give you some markers along the talk to match the time. We're 5 minutes late, so you have 5 minutes together.
Good. Thanks. So I would first like to just thank the organizers for this opportunity to share my work at this really interesting conference. Today I'm going to talk about two papers that we put out earlier this year with my supervisor Simone, where we introduce objects that are dual to Feynman integrals, which have nice properties that they extract integral coefficients when you pair them with corresponding Feynman integrals. So the topic of this talk is integral reduction. If we want to compute a scattering amplitude in perturbative quantum field theory, this has a standard expression. We would get it in terms of Feynman, a bunch of Feynman diagrams, each of which could have some messy numerator. And this makes the problem of just straightforwardly evaluating all of these integrals in a brute force manner quite difficult. So the smarter way is really to express any amplitude in terms of a linear basis of well-known master integrals. So in the case of one loop, we have a box, triangle, bubble, and tadpole, and also the possibility of a rational term. So with this basis, we just need to know how to compute these coefficients. And generalized unitarity gives us a way to do this. Essentially, it tells us that we can get these from cut matching. So, for example, the box coefficient, to extract that from an integral, we just take the quad cut of the given integral, the amplitude will factorize, and the box coefficient is a product of tree-level amplitudes. And this is particularly appealing because now what we're doing is we're building up a one-loop observable from simpler tree-level observables. Generalized unitarity also highlights an important property of Feynman integrals in which the analytic structure is really determined by their cuts. However, residue formulas for these subtopologies can be quite difficult to find, and it gets even harder when we start working in generic dimension. So our goal is to really find a systematic formalism for extracting these integral coefficients in any dimension and for all topologies in a way that maintains the spirit of generalized unitarity. Okay, so we want to perform integral reduction in generic dimension. So at least at one loop, it looks something like this, where we have a new integral, the pentagon. We've lost the rational term. That information is now contained inside the epsilon dependence of the coefficients now. And we want to do this in a way such that these C's we get these C's from residue formulas. And not only do we want them from residue formulas, we want these residue formulas to correspond with the intuition that we have from generalized unitarity. And the traditional way of coming by such a decomposition here is using integration by parts identities. And while we have extremely efficient algorithms to do this, they're still a black box. They don't give us a great intuition for when or why cancellations happen. Often, propagators are also squared, so you have to do additional rounds of integration by parts, and cuts are not utilized. So this motivates us to look for additional ways to extract these C's in generic dimensions. And one way of doing this is called intersection theory, which was introduced, I guess, 3 years ago now by Zira and Australia. And the first step here is really to realize that Feynman integrals are not unique. They are, you can always shift them by a total derivative, which is the same thing as an integration by parts identity. And so what we want to realize is that the salient information contained in a given Feynman integrand is actually given by its cohomology class. That is, we should be looking at Feynman integrals modulo all integration by parts identities. So this starts, we start off on the right foot in this way, since if we're talking about things that are, if we're talking about cohomology classes, then everything we talk about is manifestly independent of integration by parts identities. Moreover, this cohomology always automatically just comes with a dual cohomology associated to it. And we can take the cohomology and its dual, and we can pair them to get an inner product. This inner product is called the intersection number, and it's simply defined. You just take an element from the cohomology and an element from the dual cohomology, you wedge them together, and you integrate over the whole manifold. So once we have specified, for example, an orthonormal basis for the cohomology as well as the dual cohomology, we could write down a resolution of identity, much like in sort of elementary quantum mechanics. And then given any Feynman integral, we can write that as a linear combination of our basis integrals, just by applying this resolution of identity, where this inner product is now giving us our integral coefficients. And moreover, this inner product is an algebraic operation. It's just a bunch of nested residues. So intersection theory already tells us that we're on the right track, in the sense that we can compute these C's as residues. It's just a bunch of residues. Okay, and the thing that we have to understand is what is the dual space and how do cuts fit into that. Right, so the dual space, well, there is a sort of unsatisfactory answer to this, to what it is. And this dual space is sort of, it's well known in the math literature, but it's well known for a deformed problem. It's well known for the problem when you only have branch cuts. So what people have done in the past is they've deformed the Feynman integrals such that all propagators are raised to some non-integer power, say alpha times epsilon. And this takes all of our poles and it turns them into branch points. And then we take the intersection number, extract our integral coefficient, and take the deformation parameter to 0 at the end of the calculation. And now this works, but it's missing it's missing the spirit of generalizing unitarity, in the sense that this deformation obscures the connection of the proportion of propagators to branch points just obscures any connection to generalized unitarity cuts. Okay, so the whole point of this talk is to really just tell you what is the undeformed dual space. So the undeformed dual space is given by some quite simple objects in some sense. They turn out to be, all the dual forms, they turn out to be localized to generalized unitarity cuts. So if I have a propagator on the Feynman integral side, that becomes a boundary or a zero on the dual side, and these are zeros at the on-shell conditions where the propagators are on-shell. And so essentially this dual cohomology is populated by differential forms that have compact support around on these generalized unitarity cuts. So the dual cohomology is actually spanned by holomorphic forms multiplied either by a Heaviside theta function, which has support away from one of these singular points, or its derivative, which has support on a little ring around one of these singular points, and this just takes a residue. And for every propagator, we need to have a theta or a d theta to ensure this compact support condition. Okay, so a generic element of this dual space looks something like this. It turns out that the one loop forms in dimensional regularization are actually 5 forms. We have the differential for the 4 physical loop momentum, but we also have this extra guy, which is the differential of the radius of the -2 epsilon dimensional part of the loop momentum space. So it's a 5 form. And if we don't take any cuts, the cohomology is actually empty. So the first sort of non-trivial element that we can have is a 4 form that is restricted or localized to a 1 cut. So this would be something like a tadpole dual. And then we have all the way down to a 0 form on it that is localized to a 5 cut. So this would be the pentagon dual. And so the complexity is sort of inverted from the normal Feynman integral perspective, in the sense that for Feynman integrals, this pentagon would be the most complicated object. But here on the dual side, it's actually the simplest because it contains 5 d thetas. So it's a fully localized object. It'll just take a bunch of residues. On the other hand, this tadpole only contains 1 d theta, so it turns out to be actually the most complicated object. Okay, so now that we've understood sort of a little bit of what these dual forms look like, I want to explain how they simplify the calculation of the intersection number and in turn the extraction of integral coefficients. So let's consider the box coefficient, for example. We put here the box dual form, which is localized to this box cut. So that means it has 4 powers of d theta. These 4 d thetas are going to turn into a residue on the quad cut of whatever amplitude is on the right-hand side here. This will in turn factorize whatever's this amplitude on the right-hand side. So that means that we only ever need to know the expression for these amplitudes on their cuts. So we don't need to know the whole integrand. But as I was stressing before, the one loop space forms, they're actually a 5 form. So this d theta is only 4, so there's still something else left. There's a leftover part. So on the leftover part, we have some form. It looks something roughly like this, and it's actually the image of this form under something called the CMAP. It's not so important to understand what this is. The only important thing to take away is that not only do we need the dual forms to be compactly supported on the propagators, we also need them to have compact support around any branch points. And this is what this CMAP does. It just makes sure everything has the correct compact support. So when everything's all said and done, this leftover piece will have some d thetas at the branch points, and that will take additional residues. And in the end, we obtain the box coefficient, which is just a rational function of Mandelstams and epsilon. Okay, so for the remainder of the talk, I just want to describe the workflow and how to use our technology, and what are the key steps in this, namely how to compute differential equations, and a little bit more about what the CMAP is and why it's needed for computing these intersections. I also want to note that this is a relatively new technology, so we're still in the development phase, and there are certain roadblocks that we still have to overcome. For example, multivariate intersections are at the moment quite difficult, but that's not so much of a problem. We're still in the learning phase, and it's still worthwhile to figure out what are the smart choices and better algorithms for doing such things. Okay, so the first step is really just to pick a basis of dual forms. Once we've picked the basis of dual forms, the condition that it's orthogonal to some basis of Feynman integrals automatically fixes a basis of Feynman integrals for us. And it turns out that we actually never have to reference this basis of Feynman integrals from now on. So the second step is actually just what are the differential equations of these dual forms? And we can compute this differential equation just using dual integration by parts identities, which are simpler than their Feynman counterparts in the sense that they're localized to these cuts, and propagators simply don't exist on the dual side, so we're never going to square a propagator. And once we have a canonical differential equation, this orthogonality condition guarantees that the differential equation for this basis of Feynman integrals is simply the minus transpose of the dual differential equation. So then we can integrate the minus transpose of this dual integration, differential equation to get the integrals in our basis and use that to compute loop amplitudes. The other step that we need to do is make sure that everything has the correct compact support. So we go through the step, making sure everything has the right support, and then we can pair that with amplitudes or other Feynman integrals, and we will extract generalized unitarity coefficients, which will again allow us to compute loop amplitudes. Oops. So I want to just spend some time going over this step 2 and this step 3, and just giving it a little bit more intuition for what's happening there. In particular, I want to illustrate why these dual differential equations are actually transposed instead of in opposition to the Feynman side. Because normally, if we take a Feynman integral, say some of the more complicated topologies like a box, and we take its derivative, we're going to find the triangle and the bubble, right? On the dual side, it's actually reversed. We take a derivative of some simpler topology, we're going to find some more complicated topologies. And the reason why is quite simple. And let's take a look at this bubble dual form. So it's localized to the bubble cut, and it also needs to have a theta function that is enforcing compact support around the triangle propagator as well. So if we take the derivative of this, we're going to get a derivative hitting this theta function. So then this d theta wedge, this localized dual form, will actually localize even further to the triangle cut. So that's why things are transposed. So and things were these integration by parts relations were sufficiently simple that we were able to obtain a canonical differential equation in generic dimensions for any one loop dual form and equivalently Feynman integral. Okay, so the second thing I want to expand on is what why we need to go through this compactifying procedure. So as I said back at the beginning of this talk, the intersection number is simply defined. It's just I take an element from the Feynman integral space, Feynman form, and a dual form, and I wedge them together, integrate over the full space. And for this to be an actual well-defined operation, this dual form has to have compact support around the singularities of my Feynman integral. Otherwise, it would just be nonsense. And so if we, for example, start with a dual form that has compact support just around the propagators, we can't plug that into this intersection formula. But there always exists a form that has compact support around the branches and the propagators that is co-homologous to the original one we were given with. So the difference between these two is some total derivative, which means that they're equivalent in cohomology. And the way that you build such a compact supported form is you just start with whatever you're given, and then you compute, you subtract a primitive of this thing in a little neighborhood around all of the singularities. And these primitives, they satisfy this differential equation here, but they satisfy it only as a Laurent series near these singularities. So in the one form case, it's really trivial to construct these primitives. We just have to integrate order by order in some small parameter, which is the distance away from these singularities. But things get a bit more complicated when we start wanting to do this for, say, a 4 form. So in practice, we have two different ways of going through this compactifying procedure for multivariate forms. One, we can use federation, which is the philosophy is kind of we do things one variable at a time. And this allows us to reuse the simplicity of the one form CMAP. However, it makes things vector valued and matrix valued, which is, I mean, it's not so much of a problem, but it's been annoying. We also have to compute the CMAP for the entire basis of dual forms all at once. And it also makes the singularity structure at infinity quite complicated. So we get singularities from Feynman diagrams from numerators. And for example, if we start with a Feynman diagram that has a double pole, and we do the intersection for one variable, we're going to be left with something that has a fourth order pole. And if we do that again with another variable, we're going to be left with something that has a sixth order pole. So this means that we have to keep computing these primitives to higher and higher order as we're peeling away these variables. So eventually, at some point, it will become intractable. And there's sort of a mixed bag thing here, which is we have even though we're computing an algebraic invariant, to actually go through the computation, there's a lot of choice that's involved. You have to choose coordinates, you have to choose bases of forms on the fibers, and you have to choose an order that you're going to integrate. So, and you can and the intermediate steps can change drastically depending on the choices you make. So we don't really understand what are the optimal choices in this procedure. The second way you can go about doing this is sort of combinatorically, and you just deal with the multivariate nature of the problem. This allows us, the positive of this is we can actually just construct the compactly supported version of a form individually. We don't need to do it for the whole basis at the same time. The sort of complication with this method is that you need to have primitives for every single way of approaching a singularity. And then you have to take primitives of those primitives, and then primitives of those primitives, until you run out of variables. So we find the sweet spot for this technique is two forms, where it's doable. And it also is sort of plagued with by choice. There's a lot of different choices you can make, and it's unclear which is the best. Okay, so now that I've talked about these two sort of key steps, we're ready to put things together and actually compute some amplitudes. So remember that these integrals we got from the integrating the minus transpose of the dual differential equation. Right, so we know all of these integrals. So now we just need to get these coefficients, but we know how to do that. That's just an intersection number. We have some dual form, which is restricted or localized to a generalized unitarity cut. That turns into a residue on the right-hand side. This means that this amplitude is going to factorize. We can compute this factorized amplitude just by gluing from cuts, just by gluing trees. And then there's some leftover piece which will contain residues, which will take a bunch of residues at the branch points of the Feynman integral. So as a proof of concept, we have reproduced the 4 and 5 point gluon amplitudes at one loop. So these are well-known results from Byrne-Dixon and Kossauer in the 90s. But sort of the more interesting thing that we did is probably we were able to systematically study the 4-dimensional limit of these formulas. So, for example, this basis of Feynman integrals is actually UV finite. So that means that the bubble coefficient, it contains three pieces of physical information. It contains a rational term, which is paired with this 2 down here. It comes with a bubble, which is pairing with this log, and a triangle, which is pairing with this log squared. And now we want to ask, how do we, what regions in loop momentum space are responsible for, like, which residues are contributing to these different orders in epsilon? And if we know that, then we can actually just isolate which residues, say, for example, are extracting the rational term, so we can extract rational terms. So the way we do this is we look at the sort of the general expression for this this bubble coefficient, this S-channel bubble coefficient, and it's a threefold residue of some triple primitive times the S-channel residue of whatever finite integral we're looking at. And if we want to, say, get the most singular term, this triangle piece here, then there's only one contribution for that. We get a residue at L perp squared equals 0, and that's sort of like the 4-dimensional limit, right? This L perp is the radius of this extra minus 2 epsilon dimensional part of the loop momentum space, and we're setting that to 0, so that's the 4-dimensional limit. And then we also get a contribution from the soft singularity of the triangle. So this makes perfect physical sense that this is where these are the residues that are contributing to this coefficient. On the sort of opposite end of the spectrum, we can look at the rational term. And this rational term, as expected, it comes from residues that localize at infinite momentum. So only terms that have these poles at infinity are going to contribute. However, it can have either a pole at you can have residues at L perp squared equals 0 or L perp squared equals infinity. And the thing that makes us think that this algorithm could be improved is that in 2008, Badger was able to extract the rational coefficients for one loop amplitudes, and he only needed the L perp squared to infinity residues. So so this comes back to this point of did we make the best choices? We don't really know. We don't know how to make the best choices at the moment yet, but there's probably a choice that would actually push this information in the top row exclusively down to the bottom row. And yeah, the next obvious goal would be to actually start looking at this at 2 loops. Okay, so let me just conclude here and give a few interesting future directions. So essentially what we have done is we've recovered generalized unitarity in arbitrary dimensions just by using some techniques from cohomology. And our first 2 papers are just really on a systematic study of one loop integrals, I mean. So it kind of like a warm-up because we're really just reproducing known results. And we were able to find a one-loop uniform transcendental basis of dual forms in any dimension, compute its differential equation. But then we constructed 4 and 5 point gluon amplitudes from their cuts as an example. And then we looked at the 4-dimensional limits and found where these where the rational terms are which residues are computing to the contributing to these rational terms. And some of the next things that we're working on is applying these ideas at 2 loop. In particular, we're looking at it in a sort of loop by loop fashion with another student at McGill. We also need to improve the efficiency of the CMAP, either by coming up with new algorithms or just understanding what are the good choices to make. And the last thing well, maybe not the last thing, but another thing that would be interesting is looking at these rational terms at 2 loops. And I mean, eventually we would really like to find some sort of diagrammatic rules that we can apply to diagrams directly that would actually extract these rational terms. And hopefully by comparing with the formulas that we get, we can figure out how to do that. So thank you.
Thank you very much for a nice talk. So are there any questions?
I would have a question if no one else has a question.
Yeah.
So you were saying, well, you write down a basis of dual forms. I mean, in practice, like how difficult or easy is it? Like if you, I mean, okay, so the examples we discussed is a bundle where you know the basis of integrals. So you know the size of the basis of dual forms. If you have a problem that hasn't been solved yet, how do you know the size of the basis of dual forms? Do you see IDPs, your dual IDPs?
Well, I mean, the first thing I would do would be either a critical point calculation or like an Euler characteristic calculation, because that will tell you the size of the cohomology. Now, of course, in degenerate like kinematic situations, sometimes this estimate, this might not be correct, but at least it's a starting point. And if you're in completely generic situations, it'll give you the answer bang on. And as for like asking how to, you know, what, so constructing the basis is in some sense easier because you have less things to work with when you're trying to make a basis of dual forms, right? Because you don't have propagators. What you've really got is you've just got this L perp squared.
But
and you've got L perps.
Yeah. What happens? I mean, that doesn't happen at one loop, but at two loops, if you have, for example, for a given topology that you know that there's two master or more master integrals, how would the forms look like in this case?
Right. Yeah. So the singularities that you can have are at this L perp squared restricted to some cuts. Some cuts. So this would be something that's, you know, quadratic or something. And at two loops, actually, it's a bit more complicated. I should have written this note. It's a gram matrix. Let me write like this. So G is equal to L perp squared 1 L2 perp squared minus L perp 1 dot L perp 2 squared. So we can have this guy restricted to some cut, and then we'll have some whatever form we have. And then we can have we'll have some numerator. So if we have multiple basis elements on a given cut, say like the max cut of the sunrise, we would have to take a bunch of monomials to span that space.
Any other questions?
I also have a question.
Okay.
Can you hear me?
Yeah.
Yeah.
Yeah, a very nice talk. So
Thank
in
you.
a fixed integer dimension, typically there are nice choices of numerators that one can make. Maybe they're chiral or they have some nice properties in relation to paths. Do you know if this can be kind of put together with what you're talking about, or because if those exist in a fixed dimension, they don't talk nicely to this one?
Well, so yeah, this is something. Okay, so I don't know if these type of numerators. You said they don't exist in a generic dimension, or
People have written them saying 4 dimensions. I don't know what their d-dimensional generalization is. But,
I see. Yeah. Okay. So I haven't tried to construct such things in d dimensions. But I guess the thing I want to say is that this story has natural generalization to 4 dimensions. So you could work directly in 4 dimensions and then use those numerators that are known.
I guess this approach would be more specifying the first dual and then trying to construct the integral, which is also normal.
Sorry, there was a lot of feedback. I didn't really catch that.
I can send you an email.
Okay, sure, thanks.
I guess we are through with the questions. I just thought you said something about these multivariate intersections are difficult. Is that a sign problem or more like using generalized residue theorems, or what is exactly the difficulty? Just the formula?
I think the difficulty is really just we just don't understand how to make the right choices with these algorithms.
Okay, so it's more like using generalized residue theorems in a consistent way.
Yeah, I'm not quite sure how to answer this because there is a connection with generalized residue theorems, and Stefan Weinzel had a paper on this a while back.
I know that signs, they are an issue because somehow residues attain signs, and it's a bit fitty to determine. But I was just wondering. But it's okay, fine. Thank you for the talk.
Yeah, I don't think there's a problem with like an ambiguity of sign. Yeah.
Okay. Okay. Okay, thank you for the talk. I guess this is the last talk of today, and then there's general discussions and coffee.